Now, Ehsan Totoni, one of our PhD candidates in our group, will be leading us through some new algorithm studies we've been doing for parallelization, in this case, sparse triangular linear systems.
Thank you, Eric. I'm going to talk about solution of sparse triangular linear systems. Along with my advisor, Sanjay Kala's advice, I took advice of Professor Heath in our department. Sparse triangular solution is used in many methods of linear systems and least square problems. It's oftentimes done iteratively. You have to solve the same system over and over again. In direct methods of solving linear systems, it's used after factorization of the matrix into two triangular matrices with many right-hand sides. Sometimes you do it several times to refine the same solution for better numerical conditions. In iterative methods, it's the kernel in Gauss-Seidel method, and it's the kernel in many preconditioners. For instance, one may use incomplete Cholesky before conjugate gradient, or incomplete LU factorization before GMRes, and triangular solution has to be done several times to refine the solution. And it is said that if you use these preconditioners, solving the system is 40% times faster. However, this problem has very poor parallelism. This is the recursion explaining the problem. Each X entry may depend on all the previous X entries through this equation. So you have minimal concurrency and loss of structural dependencies. You also have small work per data, just one multiply add for most entries, as you can see in this summation, just multiplying these two, Lij and Xj. Because of sparsity, some Lij's are 0, so you probably have more parallelism, but that is limited too. That's why in standard packages, what I have observed is that it's slower than sequential in many cases. I'm talking about famous packages like HYPRE, which is from Lawrence Livermore National Laboratory, and SuperLU from Lawrence Berkeley National Laboratory. These are used by scientists on different supercomputers. There had been some progress in shared memory. For instance, some recent work, 2011, by Sandia National Laboratory. They took an old algorithm and tried to improve it for recent shared memory nodes. That algorithm basically constructs a DAG of dependencies of the rows and goes through level sets of the DAG and does each level in parallel. So they have millions of barriers, and this work tried to reduce some of the barriers. So basically that's not suitable for distributed memory machines. However, it has to be done in parallel because the matrix is already distributed by the factorization or other methods, and it's not worth it to recollect the matrix, or the memory is constrained. Sometimes I've seen people using this problem as some example of using supercomputers just for memory because the computation is sequential. So this is the bottleneck of many methods. What we do here is to try to solve this problem in parallel on distributed memory machines with analysis and some features of HYPRE++. So here is the linear triangular system. This is the matrix, X, and right-hand side. If we divide the columns into blocks, 3 blocks of columns, each 3 columns, 3 processors. Different colors for the diagonal block of each processor, 3 diagonal blocks. The red ones are non-diagonal, non-zeros that cause dependencies between processors. For instance, L43 causes dependency between processor 1 and processor 2 because L44 needs the contribution of this element to continue the processing. So if we want to wait for all these to get done, so here are the dependencies. L44, this has a dependency, this one has a dependency, and this is another dependency too. So if we want to do it, consider all the dependencies, we have to do the work in sequential manner. This one get done, then this one, then the other one. However, we can observe that P1 can send the contribution of L43 sooner than completing everything, because L33 does not depend on the other two. It can calculate this one, send the contribution, then go on in execution. This happens for this one too. Processor 2 can send the contribution of L76 before doing the other rows. By doing this, we get some parallelism. So let's consider processing from top to bottom. We reorder like this. These are the independent rows. These don't depend on the other processors, and they can be done in parallel by each processor. These are the contributions that need to be sent to satisfy the dependencies. If we send this earlier, do the independent ones, send these earlier, we get some parallelism here. So this is the basis of our algorithm. There is another case. There might be some regions, some dense regions in the other parts of the matrix, far from the diagonal. If we send those regions to other processors and broadcast the X entries to those, we can calculate them in parallel. However, there is the broadcast cost, and the region should be big enough to offset that cost. Remember, these have just one multiply add per element. So what is the algorithm? First, we analyze, then we solve the system as many times as we need. The analysis needs to be done just once, as is the case for previous work of parallel solution of triangular systems. So what is the analysis? First, we mark the dependent rows. A row is dependent on one processor if it has some element on the left, which makes it directly dependent on other processors, or it depends on another dependent local processor. This can be determined in one single scan of the rows. Then we place the independent rows together to have efficient sequential execution. We cannot afford to have overheads here, indirections in the execution of this problem. And we place them in backward order, respecting the local dependencies. We try to place the last one first. If it had dependent on others, we have to put them first. This is because we want to send the dependencies on the diagonal first, because they might be on the critical path. The diagonal is usually on the critical path of the progress. Then we divide the dense regions and send to other processors to have more concurrency. In the solve stage, we first try to see if there are messages received. This can happen because we are going to have virtualization and multiple blocks per processor. So we first process the messages, which might be on the critical path, then compute the independent rows with the early send of dependencies. As soon as the dependency of the next block is satisfied, we just send the contributions. Then we wait for the other messages required for this block. So this is the overview of the algorithm. We have implemented it in Charm++. A char array is created for blocks of columns. We have virtualization here because it's very important to, while one block is waiting for data, the other block can continue the execution. We use the built-in round-robin mapping, which is like a couple of lines of code to specify in Charm++. We have the priority of data messages over computation of other blocks because of faster progress in the computation. We have message aggregation or message grouping as the previous talk, because each contribution is just one floating point. We cannot send it over the network just like that. And one point is that virtualization ratio is very important. By having virtualization, we are going to have overlap of communication and computation. However, if we have too much virtualization, it's too much overhead. And if we chop up the matrix too finely, we're going to have some elements going out of the diagonal blocks of processors, which will create more dependencies. So there's the trade-off here. So before going to the results, let's see if we can implement it in MPI2. It's certainly possible because in principle every charm program can be implemented in MPI because we build a charm on top of MPI too. However, sometimes the effort might be too high. In this case, the effort is high, but it's possible. It's not too high. However, one thing is that we have to create the illusion of virtualization, the management of multiple blocks of columns per processor, and the mapping of round-robin mapping of those columns among processors, which might be too costly in terms of programmer productivity. We also need MPI HYPRE for prioritizing the data messages over the computation, which is kind of error-prone to have in the code. If we give up virtualization, we're going to have easier programming, but some performance loss. We are just using the fact that the analysis finds independent rows. We are not going to use the overlap features of the algorithm. To evaluate this algorithm, it's very important to understand that the performance highly depends on the matrix structure, as is the case with many numerical methods. We use real application matrices. We use many different ones from different application domains to capture different cases. And we have a strong scaling. We have pretty small matrices. One of them is actually just 5 megabytes in total, like 500,000 elements. We scale up to 512 nodes of BGP at Argonne, 1 core per node, simple sequential kernel. The kernel can be replaced easily in the code. We compare with the standard packages, HYPRE and SuperLU. So what are the matrices? How do we describe them? What are the differences? This table shows some of those matrices. There are a lot of them. The name, the dimension, the number of rows and columns the matrix may have. We also keep track of the number of independent rows to be able to understand the performance of each matrix. This one shows the amount of parallelism in the matrix. The number of non-zeros, the number of non-diagonal non-zeros, the non-zeros that are not in the diagonal regions of each processor. These might give us some dense regions and more parallelism. And this is the application domain. As you can see, circuit simulation, optimization, fluid dynamics, and so on. And in terms of the structure, these two are mostly diagonal, but this one is very good for getting parallelism. This one is highly sequential because of the dependencies. This one is very good too. These others are good too, but they have different structures. This one, this region is calculated, then broadcast to this region. These pieces are done in parallel, and so on. So let's see the scaling results. This graph looks scary, but it's not. Each one of these is a different matrix. We have several different matrices. And as you can see, the performance is very different for each of those. Y-axis, the speed up. X-axis, number of processors, up to 512. As you can see, some matrices have very good scaling, up to like 165 speed up on 512 processors. Some have moderate, like 10, 20, less than 10 parallelism. Some very poor, like the algorithm cannot extract any parallelism in those.
The speed up with respect to sequential?
Sequential.
All one processor.
Actually, the algorithm is in a way that one processor boils down to a sequential, simple two-loop kernel. So there is no difference in that. So this one was on no-fill incomplete LU matrices. The matrices that are fed to incomplete LU factorization code, which are going to have the same structure as the original matrix. On complete LU matrices, the matrices has gone through the factorization. The structure is different, and this is the scaling of those matrices. At some point, we see superlinear speed up because of the cache effects. As I said, the matrices are small, which is kind of interesting. For the problem that people see as sequential, sometimes we are going to have superlinear speed up. And on average, we see that the scaling is better than those than incomplete LU matrices because I use SuperLU. SuperLU reorders the non-zeros, reorders the rows, drops some of the small non-zeros. So the structure is different, and it turns out that it's good for our algorithm too. Now we compare to HYPRE, which is the package from Livermore. The blue lines are the scaling of HYPRE. As you can see, it cannot scale, and it's self-related speed up with the code running on one processor, which turns out to be not very different than the good sequential kernel.
So in other words, HYPRE on one processor and your code on one processor.
They have similar timing, very similar timing.
Okay. It's always good to see those timings actually. That even if it's 1.05, it's good to see that.
Yeah, but the difference is so big here that that 05 may not contribute much. So as you can see, HYPRE's performance is very similar to sequential. I went down to the code. I saw that the code is actually sequential. This processor computes, send the result to the next, and so on. So we don't expect much out of that code. Some performance improvement here because of cache effects. For the same matrices, we can actually get good speed ups. So this is the comparison of our algorithm. To SuperLU, this is still self-related speed up. However, SuperLU's sequential running on one processor, the same code, is very slow compared to ours. So this is actually very optimistic comparison here. SuperLU is very slow here, up to like 100 times slower than sequential, even comparing to its own sequential. Even though we can capture very good parallelism. For instance, here, SuperLU for this matrix is 221 times slower than sequential, while we get 48 times speed up. So there's a huge difference. One concern about this kind of algorithms is that the analysis phase might be too costly, that I need to have many iterations to compensate for that analysis time. This is the case for that algorithm I just told you that constructs the DAG, because that it needs all the matrix to construct a good DAG of the dependencies. Here, we do not need that DAG because each processor can get the dependencies of its local blocks of columns independent of the other processors, with just little information that just is there some non-zero on the left or not. That's it. So the analysis time scales with the number of processors. It's not perfect here because I didn't care much about the implementation. The results were good enough. And as you can see, it's often less than a single solve, the timing of analysis phase. So we do not need like several iterations to compensate for that. And it scales with the number of processors. So even with one solve after the factorization, using this algorithm is worth it than using sequential ones or other parallel algorithms. So to conclude here, parallel solution of sparse triangular linear systems is needed for many solvers. It's notoriously hard to parallelize. We have a novel algorithm that uses many heuristics, getting independent rows, putting them in backward order, sending their dependencies early, get the dense regions. That our algorithm tries to adapt to the structure of the matrix to extract as much parallelism as possible. We had an implementation in Charm++, and we made best use of features such as virtualization to get more performance. And as we saw, having these features is hard in MPI or other programming languages, as far as I know. For feature work, I just used a basic round robin to have better work balance and computation communication overlap. But better, more intelligent mapping of columns to processors might have better balance, less communication latency. By the way, this algorithm is very sensitive to communication latency because of the dependencies. And the messages are usually not too large, very small. As I said, we have message grouping here too. Smarter priorities are important here too, to have priority over different messages, data messages, different computations which might be on the critical path, and so on. Better ways to have to determine good virtualization ratio is important here too, because the performance is quite different with different virtualization ratios. For my results, I just used 4. It was a good number, 4 for everything. However, I could see that on large number of processors and small matrices, 4 is not a good number. It's too high. Or for small processors, it's too small. This is the future work. For message aggregation, as I said, latency is very important. Better aggregation of messages and being more smart in the way that understanding this message is more important, this piece of data is more important, it's on the critical path, we need to send it sooner. This has to be done too. In my code, I just wrote a very simple library to do this for me, message aggregation. And I called the flush at several points that I thought they are important. And because of the locality, in the previous talk, we heard that for each char, there is 1 buffer. Here, I just maintained like 5 buffers because because of the structure, the rows that are very close to each other might send to the same destination. So it wasn't very critical in terms of memory, but it was critical in terms of latency. And I think that's it. If you have any questions.
What's the number of messages? Is the number of messages the same as number of non-zeros basically?
If you don't aggregate, no, it's not the same as number of non-zeros, because you have several non-zeros on the same row. If you have this row here, this one will send, and some non-zeros here, this one will send just 1 floating point to the right.
But still, it's pretty large number of
Pretty large, yeah. It's very large.
So you said HYPRE was error prone in passing. Is that an MPI issue, or is that just it's hard to program it correctly?
I think because of the things I've heard, it's hard to program. I'm not going to do that, because at first I thought I would do an implementation in MPI and compare, but I asked around doing this kind of priorities in MPI, having MPI probe everywhere is going to be hard to code. It's not error prone in terms of a bad implementation in MPI. It's kind of tricky to use.
Okay, no, I don't know if you talked to Torsten, but there is actually a problem in the current MPI standard with probe if you're doing multi-threaded stuff. But I just didn't know if that was the issue or if it was just sort of obnoxious, which is fair criticism.
In Char++, just 1 line of priorities was enough for me. So I didn't care to look at that one.
So you showed some really extreme slowdowns for SuperLU and maybe HYPRE. Do you have a sense for the kind of matrices and processor numbers that we're talking about, of how long it would take to actually do the matrix reconstruction and solve serially?
To actually gather all the data together in one process.
Like if there was an algorithm that instead of trying to do SuperLU and solve it in parallel, it was just, gather to one processor and do the serial solve and then redistribute. Like, how much of a slowdown would that be? Do you have any sense of that?
I don't have much sense of that, but it depends on the computation of the machine. But I don't see why people would do that, because in HYPRE it's close to sequential if you do it just sequentially across processors. Because there isn't much communication overhead here. So
it means that if your input is already distributed across the processor cores, because it came from a different phase.
So the non-zero structure of matrix, analyzing that in analytics, that's been done before, right? Do you know if HYPRE and SuperReordering do something like that?
Actually, HYPRE doesn't do anything. It just does it sequentially. SuperReordering has the information in the factorization, has some information actually in the symbolic factorization phase, but it's not very intelligent. As far as I see, it's like simple 2D decomposition. That's it.
But if it's actually doing the non-zero structure analysis of non-zero structure, then it should be doing the same kind of, like, so the benefit, the obvious benefit, the need to do non-zero analysis would be to see what messages get sent out right away. So really doing the analysis, not exploiting the information you get.
I think it doesn't exploit any information. I didn't see much. The code is kind of complicated.